So here we are, Lecture 5, the capstone of this series on AI in railways and system assurance. Before we dive in, let's take a quick breath and look at the road we've already traveled. In Lecture 1, we laid the groundwork, what AI actually is, and where it's starting to show up across the rail environment. Lecture 2 took us into the CNELEC RAMS framework, EN 50126, 50128, 50129, the core safety standards that underpin everything we do in this industry. Lecture 3 zoomed out to AI-specific regulation, ISO/IEC FAR 2001, 23894, the EU AI Act, and RSSB guidance. And Lecture 4 brought us into maintenance, vision systems, predictive analytics, optimization tools. Now in Lecture 5, we make the shift to operations and traffic management. This is where things get real-time, dynamic, high stakes. This is the layer of the railway that keeps trains moving, coordinates resources on the fly, and holds the whole network together when it's under pressure. And this is also where AI stops being a back-office tool and starts sitting right next to the people making live decisions. Think about who we're talking about. The controller on the radio, managing a disruption in real time, the planner at the desk, balancing a timetable against a dozen competing constraints, the crew booking system, quietly working out who goes where and when. These aren't abstract systems. These are human environments. And that changes everything. Because once AI enters that space, we're not just talking about algorithms and assurance frameworks anymore. We're talking about trust, we're talking about situation awareness, we're talking about automation bias, and what happens when a human starts deferring to a system just because it sounds confident. Human factors become every bit as important as the technical standards, and we need to take both seriously. So here's what you'll walk away with by the end of this lecture. First, a solid understanding of the three major families of operational AI: timetabling, traffic management, and rostering. Second, a clear picture of how AI changes the human operator's role and what that shift means for safety. And third, an appreciation of why assurance for operational AI is a fundamentally different challenge compared to maintenance AI. These are not small distinctions. Let's get into it. So why does operations matter so much when we're talking about AI in rail? Let me give you a sense of the scale of the problem we are actually dealing with. A railway is, at its core, a massively complex scheduling and optimization challenge. And when I say complex, I mean it in the mathematical sense, not just complicated. These are problems with thousands of interacting variables, competing constraints, and consequences that ripple across the entire network the moment something goes wrong. Let's put some numbers to it. At a typical major operator, you've got over 1,000 train paths to schedule every single day. Each one comes with its own web of constraints: crew availability, rolling stock readiness, passenger demand, freight contracts, infrastructure capacity. Pull on one thread and you affect a dozen others. Then you've got over 500 crew members who need to be assigned to services. And that's not just a matching exercise. You have to respect working time regulations. Under EU working time rules, duty is capped at 10 hours per day, with mandatory minimum rest periods between shifts. You have to account for licensing. Not every driver is qualified for every route. And on top of that, you've got personal constraints that vary from person to person. Layer on top of that over 100 rolling stock units that need to be deployed in a way that matches service demand and still keeps maintenance schedules on track. And then, because nothing ever goes entirely to plan, you've got hundreds of disruptions every year. Signal failures, severe weather, rolling stock breakdowns, crew sickness, each one triggering a replanning exercise under pressure in real time. Now, traditionally, how has the industry handled this? A team of experienced planners would spend weeks, sometimes months, designing the annual timetable, testing it manually, running basic simulations, iterating. It's skilled, painstaking work. And when a disruption hits during live operations, controllers would spend hours, sometimes days, working through the rescheduling. Cascading delays, cancellations. The knock-on effects spreading further than the original fault. Crew rosters, a mix of manual work and basic software, functional but prone to errors, and in some cases regulatory violations that only get caught after the fact. That's the baseline, that's the world AI is stepping into. So what changes? With automatic timetable generation using optimization solvers, what once took weeks of manual design can now produce multiple viable timetable options in hours or days. Not one option, multiple options for planners to evaluate and choose from. When a disruption hits, Real-time AI systems can surface recommended recovery actions in seconds, not the minutes or hours it takes a controller to manually work through the options. Seconds. That's a fundamentally different operating rhythm. And crew rostering using constraint satisfaction methods and machine learning can generate compliant, near optimal rosters in minutes. Rosters that would have taken teams of people days to produce manually. The payoff from all of this is real and it's multidimensional. Better timetables, more robust, more efficient, built to absorb disruption rather than collapse under it. Faster recovery when disruptions do occur, with less delay propagation across the network. Better utilization of both crew and rolling stock, which means cost savings and improved service quality. And critically for this course, improved safety, fewer working time regulation violations, fewer human errors introduced by fatigue, time pressure, or information overload. That's why this matters. That's the problem AI is being asked to solve. Before we get into the detail of how operational AI actually works, it's worth pausing to draw a clear distinction. Use operational AI and maintenance AI are not just different applications of the same idea. They're operating in fundamentally different environments under fundamentally different pressures, and that has real consequences for how we assure them. Cast your mind back to Lecture 4. Maintenance AI is, at its heart, a detection and prediction tool. It's looking for defects, forecasting failures, optimizing when and how maintenance work gets done, and crucially, it has time on its side. These systems can work offline, in batch mode. A prediction might be generated hours or even days before any action needs to be taken. The impact of a maintenance decision is gradual. You decide to replace a bearing, that work plays out over days or weeks. If the model gets it slightly wrong, there's usually room to catch it before it matters. The assurance focus for maintenance AI reflects that. We're asking questions like, is the training data clean and representative? Is the model accurate enough? Is it operating within its defined operational design domain? Is there a monitoring process to catch drift over time? These are important questions, but they're questions we can answer largely offline with the luxury of time and iteration. Now contrast that with operational AI. The purpose here is fundamentally different: scheduling trains, resolving conflicts, optimizing resource allocation across a live network. And the timing? There's no batch mode here. These systems are running in real time, online, responding to disruptions as they happen. We're talking seconds, sometimes minutes, not hours, and the impact is immediate. A traffic management decision doesn't play out over days, it affects train movements right now. A wrong call propagates through the network in real time before anyone has a chance to intervene. That shift in timing and impact changes everything about how we think about assurance. For operational AI, validating model accuracy offline is necessary, but it is nowhere near sufficient. You also have to ask a completely different set of questions. Can a controller actually understand what the system is recommending quickly enough to act on it under time pressure? Because if the recommendation is a black box, it's not a decision support tool, it's just noise. Are the hard safety constraints truly enforced? Not advisory, not soft limits that can be overridden with a click, hard constraints. A system that can recommend a crew assignment that violates working time regulations even once is a system that has failed at a fundamental level. What happens when the AI fails? Because it will, at some point. Is there a credible fallback? Can controllers resume full manual control without losing situational awareness? That transition from AI assisted to fully manual needs to be designed, tested, and practiced, not assumed. And are regulatory constraints always respected in real time without exception? Working time rules, route licensing, infrastructure capacity limits. These aren't optional guardrails, they're legal and safety requirements, and the system has to treat them that way. That's the key implication here. Operational AI doesn't just need a different set of tools, it needs a different assurance mindset, one that puts the human operator, their cognitive load, and their ability to stay in control at the very center of the design. So let's get into the three main categories of operational AI, and I want to walk through each one with a real sense of what it actually does in practice, not just what it is in theory. The first category is timetable design and robustness. This is the planning layer. The annual or seasonal schedule, which services run when, on which routes, with how many trains, with how many crew. It's one of the most complex optimization problems in the industry, and traditionally, it's been almost entirely manual. AI changes that in a few important ways. First, it can automatically generate candidate timetables given demand forecasts and infrastructure constraints. Second, it can detect conflicts, two trains assigned to the same track at the same time, for example, before they ever make it into a live timetable. And third, and this is where it gets genuinely powerful, it can simulate the timetable under thousands of disruption scenarios, testing its robustness, identifying the weak points before the timetable ever goes live. Machine learning can even predict which disruption scenarios are most likely based on years of historical incident data. Here's what that looks like in practice. A traditional manual timetable process takes around 3 months. An AI assisted process can generate 5 candidate timetables in 2 weeks, each one complete with robustness metrics. Planners then review those options and choose the best one with confidence that it has already been thoroughly stress tested. That's a significant shift, not just in speed, but in the quality of evidence behind the decision. The second category is real time traffic management. If timetable design is the planning layer, this is the live operations layer. This is what happens when things go wrong. A signal fails, a train breaks down, weather hits the network, and the question becomes, how do you respond fast enough to limit the damage? AI helps in a sequence of steps. It detects problems early using data from infrastructure sensors and train systems, often before the controller has even been notified. It then rapidly analyzes the impact, which trains are affected, how much delay is likely to propagate, and where. It generates remedial options, reroute via an alternative line, delay this service by a set number of minutes, cancel this service, and offer alternatives. And then it ranks those options, recommending the one that minimizes overall delay and cost across the network. The controller remains in charge throughout, but the time it takes to reach a confident decision shrinks dramatically. Here's a concrete example. A signal fails on the main line. Without AI, a controller has to manually work through the options. Which trains are affected? Can I reroute them? What's the capacity on the alternative routes? That process takes 20 to 30 minutes, during which delays are already propagating. With AI, recommendations appear in around 2 minutes, something like reroute services A, B, and C to the loop line, delay service D by 18 minutes, cancel service E, and arrange passenger alternatives. The controller reviews that recommendation against the latest real world context, approves it, modifies it, or overrides it if something on the ground doesn't match the system's picture. But the heavy analytical lifting has already been done. The third category is crew and rolling stock rostering. This is the resource allocation layer, assigning the right crew and the right trains to the right services while respecting a complex web of constraints, working time regulations, route licensing, individual availability, maintenance schedules for rolling stock. It's painstaking work, and when something changes at short notice, it has to be redone quickly. AI helps by automatically generating feasible rosters, meaning rosters with no regulation violations and full service coverage. It optimizes those rosters for cost and fairness, and critically, it can revise them rapidly when disruptions hit. A crew member calls in sick, a train is taken out of service unexpectedly. The roster needs to be rebuilt fast without cutting corners on compliance. Here's what that looks like in practice. A crew member calls in sick on the morning of a shift. Without AI, a crew controller spends 1 to 2 hours manually reassigning services, checking each decision against working time rules and licensing requirements as they go. It's high pressure, detail intensive work, and it's exactly the kind of task where human error creeps in. With AI, a revised roster is generated in around 5 minutes, every service covered, no regulation violations. The crew controller reviews it, approves it, and moves on. That's not replacing the crew controller's judgment, that's giving them the space to actually use it. Let's talk about timetable design in a bit more depth, because on the surface, It sounds straightforward. Work out which trains run and when. But underneath that, it's one of the hardest combinatorial optimization problems in the entire field of operations research, and I want to show you why. Here's the problem in concrete terms. You've got passenger and freight demand to satisfy. Say 2,000 passengers want to travel from London to Manchester between 8 and 9 in the morning. You've got infrastructure capacity to respect one mainline track capacity of 24 trains per hour. You've got rolling stock availability, 10 trains available for this route, each needing 2 hours for a full round trip. You've got crew legality constraints. A crew member can work a maximum of 10 hours per day. And you've got service standards to meet, hourly frequency on major routes, for example. Now, given all of that, you have to answer some deceptively simple sounding questions. Which train services run and when? Which routes do they take? Where do services interact and how are conflicts resolved when they do? The timetable is the answer to all of those questions simultaneously. A conflict free schedule that satisfies demand, respects capacity, and obeys every constraint all at the same time. So, why is that so hard? First, the number of possible timetables is astronomically large. We're not talking about picking from a short list of options. We're talking about a solution space so vast that you couldn't explore it exhaustively even with significant computing power. Second, adding a single new service doesn't just affect that service, it shares infrastructure with other services. That creates conflicts. Those conflicts require changes elsewhere. Those changes create new conflicts. It cascades. And third, optimizing for cost while satisfying every constraint simultaneously is what mathematicians call NP hard, which in plain terms means there is no known algorithm that can guarantee finding the perfect solution quickly. You're always working with approximations and trade offs. Traditionally, planners have handled this with experience, trial and error, and hard won intuition. It takes weeks, sometimes months. The result is usually feasible, meaning it works. It doesn't have obvious conflicts, but it's rarely optimal. There are almost always efficiency gains left on the table. That's where AI comes in. Constraint satisfaction and optimization solvers, things like integer linear programming and genetic algorithms, can explore that vast solution space algorithmically. They don't get tired. They don't rely on intuition or habit. They systematically search for near optimal solutions faster than any manual process could. And crucially, they can generate multiple candidate timetables at once. So instead of arriving at one solution after months of work, planners can compare several strong options, each with its own performance metrics, and make an informed choice between them. That's a fundamentally different way of working. So we've talked about how a timetable gets designed, but here's the thing. Even a well-designed timetable can fall apart under pressure. A signal failure at the wrong junction, a train running late at a critical interchange, weather hitting a key stretch of line, any of these can cascade, and if the timetable isn't built to absorb that kind of stress, the whole network feels it. That's what robustness analysis is for. The idea is straightforward. Before a timetable ever goes live, you test it, not just on paper, but under realistic disruption conditions. Here's how the process works. You take a candidate timetable, you run it through a detailed simulation model of the railway network, one that captures infrastructure, signaling, and capacity constraints. Then you start injecting disruptions. A signal failure at 10:30, lasting 45 minutes, a train held at a platform for an unplanned dwell, a track section taken out of service. You observe what happens, which trains are delayed, by how much, do any services fail to run at all, and then you repeat that hundreds of times, sometimes thousands. What comes out the other side is genuinely useful. You get robustness metrics, something like this timetable experiences delays of more than 30 minutes in 15% of simulated scenarios. In 2% of scenarios, a service is cancelled entirely. That's not a vague sense that the timetable is risky, that's a number, something a planner can actually work with. You also get identification of weak points. Junction X is a bottleneck. Adding one more service through there would make the whole timetable fragile, and you get concrete recommendations for improvement. Add a passing loop here, shift one service earlier, reduce frequency on this route during the peak window. Now, this is where machine learning adds another layer. Historical incident data tells us which disruptions are actually likely, not just theoretically possible. Signal failures are more common on older infrastructure. Certain junctions have a history of congestion during peak hours. Machine learning can use that data to predict disruption likelihood and prioritize the simulation scenarios accordingly. Test the most probable disruptions first, focus the analytical effort where the real world risk is highest, and over time, the system learns from the simulations themselves. It starts to identify which features of a timetable design tend to make it more robust and which ones tend to make it fragile. The benefit of all of this is something quite fundamental. Without robustness analysis, you discover that a timetable is fragile when it fails in live service in front of passengers. With robustness analysis, you discover the fragility during design, before deployment, before it costs anyone anything. That's not just an efficiency gain, that's a qualitatively better way of making decisions. When a disruption hits, the railway shifts into reactive mode and the window of opportunity is narrow, really narrow. Here's why that matters. Every minute you delay your response is a minute that delay is propagating through the network. Earlier services have taken up platform capacity, track capacity, later services start to back up behind them. And if the response is poor, suboptimal rerouting, unnecessary cancellations, you're not just dealing with a technical problem anymore. You're dealing with passenger dissatisfaction, revenue loss, reputational damage. The cost of a slow or clumsy response compounds quickly. So let's look at how this has traditionally been handled. A controller monitors the network, notices something is wrong. They then manually work through the options: which trains can be rerouted, where to, what's the capacity on the alternative routes, which services have to be cancelled. They make those decisions, communicate the changes to drivers, crew, and passengers, and gradually stabilize the situation. That process, from problem detected to network stabilized, typically takes 30 to 60 minutes, during which delay is spreading. Now let's look at the same scenario with AI in the loop. Sensors detect the problem automatically. We're talking seconds, not minutes. An AI impact model then predicts the effects across the network in around 30 seconds. AI scenario analysis evaluates 10 or more possible response actions and their likely outcomes in around 2 minutes. And then a recommendation surfaces. Something like reroute services A, B, and C to the loop line, delay service D by 20 minutes, cancel service E, and offer passenger alternatives on routes X, Y, and Z. The controller reviews that recommendation, checks it against the real world operational picture, verifies it makes sense on the ground, and approves it. That review takes around 5 minutes. Implementation follows in another 5 to 10. Total time from disruption detected to actions implemented: 20 to 25 minutes. Compare that to 30 to 60 minutes manually. And crucially, the quality of the response is better too, because the AI has evaluated 10 or more options, not just the first viable one the controller could think of under pressure. Now, here is the key insight, and I want to be very clear about this. The AI is not making the decision, the controller is. The AI is doing the analytical heavy lifting, rapidly evaluating the option space so that when the controller does make a call, they're making it with better information, faster. That's the distinction that matters, not automation, augmentation. So, how does real time traffic management AI actually work under the hood? It's not one single system, it's several AI techniques working together, each handling a different part of the problem. Let's walk through them. The first is anomaly detection. Infrastructure sensors are continuously monitoring the network all the time. Voltage levels on power lines, axle box temperatures on trains, signal status patterns. Machine learning algorithms study that data over time and build a picture of what normal looks like. So when something deviates significantly from that picture, an alert is raised. Here's a concrete example of why that matters. A signal's state change rate suddenly increases. It's flicking rapidly between red and green. That pattern suggests a failing relay before the signal has completely failed. The alert goes out. Controllers have time to reroute trains preemptively before the failure becomes a full disruption. That's the difference between managing a problem and being managed by it. The second technique is disruption impact modeling. Once a disruption occurs, the immediate question is, what does this actually affect? Impact models, often rule based or decision tree models, rapidly estimate the answers. Which trains are directly blocked on the failed section? Which trains are indirectly affected, waiting for platforms or junctions that are now congested downstream? And what's the estimated delay for each one? Here's what that looks like in practice. Signal X fails on the main line. The impact model surfaces something like this. Trains A, B, and C on the main line are blocked, facing delays of 30 to 45 minutes. Trains D and E on the parallel loop line are unaffected. Trains F and G further downstream are picking up around 10 minutes of delay while the main line is cleared. That assessment, which would take a controller significant time to piece together manually, is available in seconds. The third technique is scenario analysis and optimization. This is where the AI evaluates what to actually do about it. Given the current disruption and network state, it generates multiple possible response actions. Reroute via an alternative line, delay certain services to give others priority, cancel low priority services, or some combination. Reroute this one, delay that one, cancel the other. For each option, the optimization calculates total delay across the network, passenger impact, and cost. It ranks them, and it surfaces the top 3 to 5 options to the controller with the trade-offs made visible, not a single answer presented as fact. Options with evidence behind each one. And underpinning all of this is real-time data integration. None of these techniques work without current accurate data, train positions and speeds, scheduled versus actual times, crew status and availability, rolling stock status, which units are in service, which are undergoing maintenance, weather and seasonal conditions, passenger loads from ticketing systems. All of that data from multiple sources, updating continuously, needs to be fused into a single coherent picture. That's what a real-time data platform does. It's the foundation everything else sits on. And if that foundation has gaps, if data is stale, incomplete, or inaccurate, the AI recommendations built on top of it are only as good as the data feeding them. That's worth remembering. This is the most important human factors point in this entire lecture, so I want you to stay with me here. When AI enters the control room, the controller's role doesn't disappear, but it does change fundamentally. Before AI, the controller sees a problem, they think through the options, they make a decision, reroute, delay, cancel, they implement it, and they are accountable for the outcome. That's a clear, complete loop. One person, full ownership. After AI, the loop looks different. The AI detects and analyzes the problem. The AI recommends actions. The controller reviews that recommendation, verifies it makes sense against the real world operational picture, approves it or modifies it, and then it's implemented. Accountability is now shared between the controller and the system. That shift brings real benefits. Controllers can make better decisions faster because they have analytical support to lean on. Fewer human errors creep in because the AI doesn't get tired, doesn't panic under stress, doesn't have a bad day. And decision making becomes more consistent because the AI applies rules the same way every time. Those are genuine gains. But and this is where I want you to pay close attention. That same shift introduces risks that are just as real. The first risk is automation bias. This is where a controller overtrusts the AI without applying their own critical judgment. Here's what that looks like in practice. The AI recommends rerouting via a particular line, but the controller knows or should know that line is currently closed for maintenance. If they don't verify, if they just approve the recommendation because the system said so, that's automation bias. And in a safety critical environment, that kind of passive acceptance can have serious consequences. The second risk is loss of situational awareness. When controllers rely on AI summaries rather than engaging with the raw data themselves, their direct picture of the network starts to fade. And then the AI goes offline during a crisis. Suddenly, the controller has to resume full manual control, but they don't have the big picture view they need because they've been reading summaries, not the network. That's a dangerous moment. The third risk is skill atrophy. This one plays out slowly, but it's just as serious. After 5 years of working with AI assistants, a controller retires. Their replacement has never handled a major disruption without AI support. They've never had to think through the options from scratch under pressure manually. When the system fails, they don't know how. That institutional knowledge, once lost, is very hard to rebuild. The fourth risk is cognitive overload, and this one is often underestimated. A poorly designed AI interface doesn't help the controller, it overwhelms them. Too many alerts, too much raw data surfaced all at once, recommendations that are hard to interpret quickly. In a high pressure situation, that kind of interface doesn't reduce cognitive load, it adds to it. So, how do we mitigate these risks? RSSB guidance, specifically the principles from T1362, points us toward several approaches. First, transparency. The AI shouldn't just surface a recommendation, it should explain its reasoning. Why is it recommending this action? What data is it based on? A controller who understands the reasoning behind a recommendation is in a far better position to verify it than one who is simply presented with a conclusion. Second, calibrated trust. The interface should show confidence levels alongside recommendations. A recommendation at 95% confidence is a different conversation to one at 60%. When the system is uncertain, the controller needs to know that so they can apply proportionally more scrutiny. Third, active human approval. For safety critical decisions, the controller must actively approve, not passively accept. There's a meaningful difference between a controller who has genuinely evaluated a recommendation and one who has simply clicked through it. System design needs to make that distinction real. Fourth, regular training without AI. Controllers need to practice manual decision making deliberately, schedule drills, plan system outages used as training opportunities. If the only time a controller works without AI is when the AI has failed during a live disruption, that's far too late. And fifth, graceful degradation. If the AI fails, operations must be able to continue. Manual decision making has to remain a viable mode, not a theoretical fallback that nobody has actually tested. The system fails safely or it isn't safe. Let's talk about rostering, because behind every service that runs on time, there's a roster that put the right person in the right seat on the right train at the right moment. And making that happen at scale across an entire network is a genuinely complex problem. Let's start with crew rostering. Here's what a single crew member's day might look like. They start at 6 in the morning, driving service A from London to Birmingham, 2 hours. At 9, they pick up service B, Birmingham to Manchester, an hour and a half. They rest from 11:30 through to 4 in the afternoon. Then at 1600, service C, Manchester to Leeds, another 2 hours, off duty at 18:30. That looks straightforward enough on paper, but every single assignment in that day has to satisfy a web of constraints simultaneously. Working time regulations under EU rules, a cap duty at 10 hours per 24-hour period, minimum 11 hours rest between duty periods, maximum 48 hours per week. Then there's skills. The crew member has to be licensed for that specific route and that specific train type. Availability, they can't be on leave or already assigned elsewhere. Fairness, night shifts and weekend work need to be distributed equitably across the whole crew base. And cost, you want to minimize deadheading, which is where a crew member has to travel without passengers to get to or from their starting point. Every one of those factors interacts with every other. Change one assignment and you may have just violated a constraint 3 steps down the line. Now let's look at rolling stock rostering. The logic is similar, but the constraints are different. A train might start at 6 in the morning on service A, London to Birmingham, then service B at 9, Birmingham to Manchester, then service C at 1600, Manchester to Liverpool, an overnight maintenance window from 1800 through to 6 the next morning, and then straight onto service D at 6, Liverpool back to London. Again, every assignment has to satisfy its own set of constraints. Compatibility: the train type has to match the service requirements in terms of capacity, speed, and onboard equipment. Maintenance: every 5,000 kilometers or 28 days, that unit needs a scheduled maintenance window. Miss that window, and you've got a compliance problem. Availability: the unit has to be serviceable, not in repair, not already committed elsewhere. And utilization: you want to maximize the revenue hours that unit is generating and minimize the time it's moving empty. Both of these problems, crew rostering and rolling stock rostering, share the same fundamental character. They're complex combinatorial problems. There are many possible valid assignments. The constraints interact in ways that aren't always obvious. And when something goes wrong, a crew member calls in sick, a train is taken out of service, the entire roster may need to be revised quickly, under pressure, without violating any of the rules in the process. That's an extraordinarily difficult thing to do manually at speed. This is where AI brings very concrete value. Constraint satisfaction solvers and optimization algorithms can take all of those requirements, every regulation, every legality, every operational preference, and generate a valid, near optimal roster automatically. What might take a rostering team hours or even days to produce manually can be generated in minutes. And critically, the system can guarantee that regulatory and legal constraints are respected, not approximately, not mostly, guaranteed. When a disruption hits and re-rostering is needed urgently, the same process runs again: new roster, all constraints satisfied, ready for the crew controller to review and approve. That last point matters. The roster is a recommendation. The crew controller reviews it. They apply their operational knowledge and judgment. They approve it or they modify it. The AI does the heavy combinatorial lifting. The human makes the call. This is a critical assurance point, and I want to be direct about it. Rosters are not just operational documents, they are legal documents. And for crew rostering, the primary regulatory framework is the EU Working Time Regulation. Let's go through what that actually requires. Maximum duty is 10 hours in any 24-hour period, with limited exceptions for specific operations. Minimum rest between two work periods is 11 hours, with shorter rest permissible on up to 3 days per week. Maximum weekly hours are 48, averaged over a 17-week reference period, and detailed records of all work and rest periods must be maintained for every single crew member. Now, let's be clear about what non-compliance actually means, because this isn't a technical footnote. It has three distinct dimensions, and all three are serious. Legally, EU and national regulations give railway operators very little room to maneuver. Fines for violations range from 10,000 to 100,000 euros per violation. That's not an abstract risk, that's a direct financial and legal exposure. From a safety perspective, uh, fatigue impairs performance. That's not an opinion, it's one of the most well established findings in human factors research. Excessive duty hours increase the likelihood of errors, reduce reaction times, and compromise the judgment of the very people we are relying on to keep the network safe. A roster violation isn't just a paperwork problem, it's a safety risk, and reputationally, non compliance doesn't stay internal, it becomes public. Regulatory findings, enforcement actions, press coverage, the reputational damage from a pattern of working time violations is significant and lasting. So, what does this mean for how rostering AI must be designed? These constraints cannot be soft objectives. They cannot be trade offs that the optimization algorithm weighs against cost or efficiency. They are inviolable boundaries, hard limits. The system enforces them, or the system is not fit for purpose. In practice, that means several things. Before any roster is finalized, the AI runs explicit constraint checks against every crew member's assignment. Everyone, not a sample, not a spot check, every assignment, verified compliant before the roster is published, then humans review the roster before it goes live, a second set of eyes applying operational knowledge and contextual judgment to what the system has produced. After publication, post deployment audits randomly check compliance on an ongoing basis because a system that was compliant last month may have drifted. Data changes, edge cases emerge, audits catch what continuous monitoring might miss, and if a violation is found, it is investigated, root cause identified, and the AI system is retrained or reconfigured accordingly, not patched over, properly addressed. The same rigor applies to rolling stock. Maintenance intervals are not optional. Safety approvals are not negotiable. The logic is identical: hard constraints, human review, ongoing audit, because in both cases, the consequence of getting it wrong isn't just operational, it's legal, it's financial, and in the most serious cases, it's a safety event. That's why this is a critical assurance point, not a footnote. We've spent time in earlier lectures on the Synelec framework. Now let's look at how it applies specifically to operational AI, because while the framework is the same, the emphasis shifts in some important ways. Starting with AI 50126, the RAM's lifecycle standard. The first question to ask about any operational AI system is, what kind of criticality are we dealing with? And the answer shapes everything that follows. If the system is safety critical, real-time traffic management, opposing train movements, for example, then safety is the primary assurance driver, full stop. If it's operationally critical, crew rostering, on which service delivery depends, then availability and regulatory compliance become the primary drivers. And if it's regulatory critical, which crew rostering also is, given its relationship to working time rules, then compliance auditing is not optional, it's essential. For each of those categories, you conduct a hazard analysis and risk assessment. Let me give you two concrete examples of what that looks like. First hazard. The AI recommends an unsafe train movement, one that violates signaling interlocking rules. The risk is immediate and severe. Derailment, collision. The control measure is equally clear. Hard checks must verify every AI recommendation against signaling rules before any movement is executed, not after, before. Second hazard. The AI generates a roster that violates working time regulations. The risk here is twofold: legal liability on one hand and crew fatigue on the other, which, as we've discussed, is a direct safety concern. The control measures are explicit constraint enforcement within the system itself, human review before publication, and ongoing compliance audit after deployment. Now let's look at EN 50128, the software development standard. Operational AI tools, forecasting engines, optimization algorithms, scheduling systems are software, and they must be developed to software assurance standards. That means a defined specification, inputs, outputs, accuracy targets, known failure modes. It means a clear architecture. How does the system process data and how does it integrate with signaling infrastructure? It means implementation quality, code standards, testing documentation, and it means verification and validation, comprehensive testing that includes realistic and demanding scenarios, simultaneous failures, extreme weather conditions, edge cases that stress the system beyond normal operating parameters. There's also a unique challenge here that's specific to operational AI: real-time performance. A system that produces the right answer but takes 12 minutes to do it is not fit for purpose in a live disruption environment. Verification and validation, therefore, has to include performance testing under load, not just correctness testing, speed and correctness together. And finally, EN 50129, the safety case standard. Operational AI doesn't sit in isolation. It interacts with safety critical systems, signaling, automatic train protection, and the safety cases for those systems need to explicitly address the AI interface. Four questions in particular: how are AI recommendations evaluated before being executed? What hard safety constraints are enforced and by what mechanism? What happens if the AI fails? And how is human authority preserved throughout? Here's an example of how a claim in a safety case might be framed. Something like, The traffic management AI system supports controller decisions but does not override signaling interlocking. All train movements must be authorized by the interlocking before execution. Therefore, the safety of the signaling system is preserved. That last point is worth dwelling on for a moment. The AI can recommend, the interlocking authorizes. Those are two distinct functions, and keeping them distinct is what maintains the integrity of the safety architecture. The AI sits outside the safety envelope, the interlocking holds it. Let's bring everything we've discussed to life with a real deployment. A major European railway operator, a complex network, and a genuine attempt to deploy AI assisted real time traffic management at scale. Here's the context: over 2,000 train movements per day, 10 to 15 major disruptions per month, signal failures, rolling stock breakdowns, severe weather, and each disruption, before AI was introduced, took 30 to 60 minutes to stabilize, during which delay was cascading across the network, affecting thousands of passengers with every incident. The implementation was built in layers. First, a data platform, real time feeds integrated from signaling systems, train positioning, weather services, and crew scheduling, all fused into a single operational picture. Second, anomaly detection. Machine learning algorithms learned what normal looked like across the network and raised alerts when something deviated. Signal faults were being detected around 5 minutes before complete failure. 5 minutes of warning, that's the difference between a preemptive reroute and a reactive scramble. Third, impact models. Rule-based and machine learning models predicted which trains would be affected by a disruption and estimated delay magnitudes across the network. Fourth, optimization. Constraint-based algorithms generated a ranked list of remedial actions, reroute, delay, cancel, priority changes, evaluated against each other for total delay, passenger impact, and cost. Fifth, the controller interface. And this one deserves particular attention. The interface was deliberately simple: current disruption and affected services, top three recommended actions, each with predicted outcomes clearly displayed, and a manual override, always visible, always accessible. The controller could implement a different action at any point. That wasn't an afterthought, it was a design principle. Sixth, integration with signaling. Before any recommended action was presented to the controller, it was validated against the interlocking. Only feasible actions appeared on screen. The controller was never presented with a recommendation that the signaling system couldn't safely execute. So, what happened after 2 years of operation? The results were significant. Recovery time dropped from 45 minutes to 18 minutes, a 60% improvement. The number of passengers affected per disruption fell from 8,000 to 2,000, a 75% improvement. Customer complaints dropped by 70%. Controller workload during disruptions was reduced, not because controllers were doing less, but because they were doing different work. Strategic decisions rather than manual evaluation of every option from scratch, and system uptime improved from 99.2% to 99.8%, reflecting better network resilience overall. But the lessons learned are just as instructive as the headline numbers, possibly more so. The first lesson was about controller behavior. In the early months, controllers overtrusted the system. They were approving recommendations without sufficiently scrutinizing them. Automation bias, exactly as we discussed earlier, showing up in a real operational environment after around 3 months of use and a handful of recommendations that didn't account for real world context. The system couldn't see. Controllers became more critical. Verification became routine. Trust became calibrated. That shift didn't happen by accident, it happened through experience, and it reinforced why training and structured familiarization are not optional extras. The second lesson was about interface design. Early versions of the interface showed too much data. Controllers were overwhelmed rather than supported. The final interface was stripped back significantly, showing only the most critical information and the top recommendations. Less turned out to be considerably more. The third lesson was about fallback. At one point, the AI system failed due to a software bug. Operations continued smoothly because controllers had maintained their manual decision-making capability and the fallback procedures had been designed, tested, and practiced in advance. That moment validated something important. Graceful degradation isn't just a design requirement on paper, it has to work in practice. And in this case, it did. And the fourth lesson was about continuous improvement. After 6 months of live operation, real operational data was fed back into the impact models and optimization algorithms. The system learned from its own deployment. Accuracy improved. Edge cases that had produced poor recommendations early on were gradually ironed out. Taken together, this case study illustrates something that runs through this entire lecture. AI in operations delivers real, measurable value, but only when the human factors are taken as seriously as the algorithms. The technology worked, the interface design mattered just as much, the controller training mattered just as much, the fallback procedures mattered just as much. You don't get the 60% recovery time improvement without all of those things working together. Let's look at a second case study. This one is about timetable design, and it illustrates something we talked about earlier in the lecture in a very concrete way. The scenario is a mixed passenger and freight rail corridor, 200 kilometers. A new annual timetable needed to be designed. Under the traditional approach, a team of experienced planners worked on the timetable manually for 2 months. Trial and error, hard won expertise applied iteration by iteration. The final timetable was conflict free. It met demand. But here's the thing, nobody actually knew how robust it was, how it would hold up under pressure, under disruption. That was unknown until something went wrong in live service. With AI in the process, the picture looks very different. Step 1. Optimization solvers generated 10 candidate timetables in 2 weeks. Not one timetable after 2 months. 10 options in 2 weeks. Each one a viable starting point for evaluation. Step 2. Every candidate timetable was put through robustness analysis. 500 disruption scenarios each. Signal failures, rolling stock breakdowns, severe weather, crew unavailability. Each scenario simulated. Outcomes observed. Results recorded. Step 3. Weak points identified. And this is where it gets interesting. Timetable number 1, the most cost-effective option on paper, had a critical bottleneck at junction Z. When the signal there failed, 8 services were delayed by more than 30 minutes. 2 services were cancelled entirely. On paper, it looked like the best option. Under simulation, it was fragile in a very specific and dangerous way. Step 4. The AI recommended changes. Add a passing loop at the bottleneck. Shift one service earlier. Reduce frequency on one route. The timetable was redesigned accordingly and put through simulation again. Step 5. The final timetable, only 8% of simulated scenarios resulted in delays of more than 30 minutes, and the cost increase compared to the original less than 2%. Significantly more robust, almost no additional cost. The benefit here is exactly what we described when we introduced robustness analysis. Without this process, the bottleneck at junction Z would have remained hidden until a signal failed in live service, at which point 8 services delayed, 2 cancelled, with passengers on board, connections missed, knock-on effects cascading. That's when you would have discovered the fragility. With this process, it was found during design, fixed before a single train ran, before it cost anyone anything. That's not a marginal improvement. That's a fundamentally different relationship between planning and risk. Let's take a step back and bring the three applications together. Because while timetabling, real-time traffic management, and rostering all fall under the umbrella of operational AI, they're quite different in character, and those differences matter for how we assure them. Timetable design happens offline, weeks or months before operations begin. There's time for iteration, review, and expert scrutiny. And because the timetable underpins everything downstream, every service, every connection, every resource plan, the assurance bar is high. Robust validation through simulation, human expert review before anything is finalized, and the planner carries accountability for the design that goes live. The AI generates options, the planner owns the decision. Real-time traffic management is the opposite end of the spectrum. This is online, live, in the moment. Seconds to minutes. The stakes are immediate passenger experience, network performance, and in some scenarios, safety. The assurance approach reflects that urgency. Hard safety constraints that cannot be violated under any circumstances, controller override that is always possible, always accessible, and a fallback capability that allows operations to continue if the AI drops out. The controller is the final decision maker, the AI is advisory. That distinction is non-negotiable. Crew and rolling stock rostering rostering sits between the two. It happens offline, daily or weekly, but the outputs have both regulatory and operational consequences. Working time compliance is not optional, service coverage is not optional. The assurance approach is built around explicit compliance checks before publication, human review as a mandatory step, and ongoing audit after deployment. The roster planner reviews and approves before anything goes live. Accountability stays with the human. Three applications, three different timescales, three different assurance approaches, three different human roles, but one consistent principle running through all of them. The AI supports the decision, the human owns it. Before we close out this lecture, let's talk about what can go wrong. Because based on real world deployments, there are five pitfalls that come up again and again, and knowing them in advance is considerably better than discovering them in live service. Pitfall 1: over automating decisions. There's a temptation, understandable but dangerous, to make AI fully prescriptive. The system recommends rerouting trains A, B, and C and executes it automatically. No controller approval, no human in the loop. For genuinely low risk decisions, platform assignment on a simple layout, for example, that might be acceptable. But for complex decisions, rerouting through a congested junction, managing a cascading disruption, full automation without human approval is a risk that isn't justified by the efficiency gain. The mitigation is straightforward. AI recommends, controller decides. That boundary needs to be designed in, not left to operational culture to maintain. Pitfall 2: ignoring real time performance. Optimization algorithms are powerful, but power and speed are not the same thing. If an algorithm takes 10 minutes to find the best solution and the disruption needed a response 2 minutes ago, that recommendation is useless, technically correct, operationally irrelevant. The mitigation is to design explicitly for real-time performance, use fast heuristics and bounded search methods, find a good enough solution quickly rather than a perfect solution slowly. In a live disruption environment, good enough in 2 minutes beats optimal in 10 every time. Pitfall 3: weak integration with safety systems. This one has direct safety implications. The AI recommends rerouting a train via a particular line, but that line is closed for maintenance. If the recommendation hasn't been validated against signaling and automatic train protection logic before it reaches the controller is being shown an option that isn't safe to execute. That's not a decision support tool. That's a liability. The mitigation is absolute. Every AI recommendation must be validated against signaling and safety system logic before it is presented. Only feasible, safe moves appear on screen. The controller should never have to second guess whether a recommendation is physically possible. That check happens before they see it. Pitfall 4: underestimating human factors. This one is perhaps the most consistently underestimated in practice. Controllers are handed AI generated recommendations with no training on how to interpret them. The interface is cluttered with raw data. The reasoning behind the recommendations is opaque, and the result? Controllers don't trust the system, they don't understand it, and they mostly ignore it. An AI system that gets ignored is not a safety risk, but it's also not delivering any value. The investment has been wasted. The mitigation requires genuine commitment. Invest seriously in interface design. Make recommendations clear and explainable. Train controllers thoroughly before go live and continue that training as the system evolves. Gather feedback from the people actually using it and iterate. The technology is only half the system, the human using it is the other half. Pitfall 5: no fallback. If AI becomes the single source of decision support and then it fails, a software bug, a hardware failure, a network outage, controllers are left without support during the moments they need it most, and operations can become chaotic very quickly. The mitigation is graceful degradation, designed in from the start, not bolted on as an afterthought. Operations must be able to continue without AI, less efficient but safe. And critically, manual operation needs to be tested regularly. Scheduled drills, planned outages used as training exercises, because a fallback that hasn't been practiced is not really a fallback, it's an assumption. 5 pitfalls: over automation, performance gaps, weak safety integration, underestimated human factors, and absent fallback. None of them are inevitable. All of them are avoidable if they're anticipated and designed against from the beginning. Operational AI doesn't just need to work well technically, it needs to be governed well organizationally. And that means two frameworks working in parallel: EN 50716 for the technical side and ISO/IEC 42001 for the organizational side. Let's work through what each one requires in this context. Starting with EN 50716, the first requirement is data governance. Operational AI systems are ingesting real time data continuously: train positions, weather conditions, crew status, all of it feeding into recommendations that affect live operations. And the principle here is simple, but its consequences are significant. Bad data produces bad recommendations. A recommendation is only as trustworthy as the data behind it. So that data must be quality checked continuously, not just at system commissioning. Second, model training and reproducibility. The optimization and forecasting models at the heart of these systems must be trained, validated, and versioned. Every version of every model needs to be documented, and when a new model is deployed, it must be tested and formally approved before it goes anywhere near live operations. You cannot simply swap in a retrained model and hope for the best. Change is controlled, or it isn't safe. Third, operational monitoring. Once deployed, the system needs to be watched, and the KPIs need to be meaningful. For timetable robustness and demand forecasting, how accurate are the predictions actually proving to be in service? For real time traffic management, are the recommended actions genuinely improving outcomes, or is the network performing similarly with or without the recommendations? For crew rostering, is the system consistently generating WTR compliant rosters, not in testing, in live operation, day after day? These aren't one time validation questions, they're ongoing performance questions. And if the answers start to drift, that's a signal that something needs attention. Fourth, planner control. Any update to an operational AI system, a new model, a new rule set, a new data source, requires testing, impact assessment, and formal approval. The system that was validated last year may behave differently after an update. Change control exists to ensure that differences are understood before they affect live operations, not after. Now let's look at ISO/IEC 42001. This is the organizational governance layer, and it addresses questions that the technical standards don't answer on their own. First, organizational policies. How are operational AI systems developed, tested, approved, and eventually retired? Who is responsible at each stage? What are the approval criteria before a system goes live? These need to be written down, agreed upon, and consistently applied, not improvised case by case. Second, roles and responsibilities. Accountability for operational AI needs to be designated explicitly. In practice, this often means a cross functional committee: engineering, safety, operations, data science, each bringing a different lens to the governance of these systems, because no single function has the full picture on its own. Third, risk management. Operational AI risks need to be linked to enterprise risk management, not treated as purely technical risks that sit within the engineering team. If an operational AI system fails, what is the actual impact on the business, on safety, on regulatory compliance, and what mitigation is in place? These are questions that belong at an organizational level, not just in a system specification document. Here's an example of what that governance looks like when it's written into policy. Something like: all operational AI systems that feed into signaling or safety critical decisions must be subject to EN 50126 hazard analysis and risk assessment. They must be tested on realistic scenarios, including disruption scenarios before deployment. They must be monitored continuously for performance degradation in live service. Any update must go through change control and require retesting. And every system must have a documented fallback procedure so that if the AI fails, manual operation can resume safely and without confusion. That's not a wish list, that's a governance framework. And the difference between organizations that deploy operational AI safely and those that don't often comes down to whether that framework exists and whether it's actually followed. So, how do you actually get from here to there? From recognizing that operational AI could help to having a mature, trusted system running across your network? The honest answer is it takes time, typically 12 to 24 months, and it happens in five distinct phases. Let's walk through them. Phase 1, planning and feasibility, months 1 and 2. This is where you define the problem before you touch any technology. Is timetable robustness a genuine issue on your network? Are recovery times from disruptions too long? Are crew rosters frequently producing working time violations? Start by identifying the problem clearly, then quantify it. How much delay? How many complaints? What's the actual cost? Then look at your data. What exists? Is it clean enough and complete enough to train a model or run an optimizer? Because if the data isn't there or isn't trustworthy, the AI won't be either. And finally, estimate the effort and the return. What resources are needed? What's the realistic timeline? And what benefits could AI credibly deliver? Faster recovery, better timetables, compliance improvements, cost savings. The output of this phase is straightforward, a go or no go decision on the AI project before a single line of code is written. Phase 2, prototyping and validation, months 3 through 6. This is where the idea becomes something real. You choose your approach, open source optimization tools, an external vendor, or an in house build. You integrate with your existing data systems, you develop the model or optimizer, and then the most important step in this phase, you validate on historical data. Here's what that looks like in practice. You take past scenario, a signal failure in March 2023, for example, you run the AI system against it. What would it have recommended? Then you compare that to the decisions actually made at the time. Did the AI do better? Would its recommendations have reduced delay, improved outcomes? You also gather feedback from the people who will actually use the system: operators, planners, controllers. Does the recommendation make operational sense to them? Is the interface usable under pressure? The output of this phase is a proof of concept with evidence that the AI can genuinely improve outcomes, not a promise, evidence. Phase 3, safety and governance, months 7 through 9. This is where the engineering rigor comes in. You conduct your RAMS analysis under EN 50126, hazard identification, risk assessment, controls defined and documented. If the system is safety related, you develop an EN 50129 safety case, demonstrating that the identified hazards are controlled to an acceptable level. You establish your organizational governance framework, roles, responsibilities, approval criteria, change control, aligned with ISO/IEC 42001. You define your KPIs: accuracy, compliance, decision quality, and the monitoring processes that will track them in live operation. And you document the operational procedures. How do controllers and operators actually use the system? What do they do if it fails? What does fallback look like? The output of this phase is an approved safety case, a governance framework, and a set of operational procedures that are ready to be trained to. Phase 4, pilot deployment, months 10 through 12. This is where the system goes live, but in a controlled, limited scope: one shift, one route, one depot, or perhaps 25% of the network. During this phase, every KPI is tracked daily. Is the system performing as expected? Operator and controller feedback is gathered continuously. What's working, what isn't? Incident logs are maintained. Any safety or regulatory issue, however minor, is recorded and investigated. The purpose of this phase is confidence building. You're accumulating evidence that the system is safe, that it works, and that the people using it trust it. The output is validated performance data and a go ahead for wider rollout. Phase 5, rollout and continuous improvement, year 2 and beyond. The system expands gradually to the full network. Ongoing monitoring is established, weekly KPI tracking, monthly review cycles, governance procedures run continuously, change control, incident investigation, risk register updates, and the system improves over time. Operational data is collected, models are retrained, updated performance metrics are published. The output of this phase isn't a project deliverable, it's a mature, trusted operational AI system that gets better the longer it runs. 12 to 24 months. 5 phases, each one building on the last, and the organizations that do this well are the ones that resist the temptation to skip phases. The planning phase feels slow when you're eager to build. The safety and governance phase feels bureaucratic when you have a working prototype. The pilot phase feels cautious when you're confident in the system, but each phase exists because something went wrong when it was skipped. Do them all in order. Let's close out with the key insights from this lecture. Six of them, and I want to deliver these not as a summary to skim but as the ideas I'd want you to carry with you. First, operational AI is fundamentally different from maintenance AI. We established this early in the lecture, and everything that followed reinforced it. Maintenance AI detects defects, predicts failures, works offline with time on its side. Operational AI does something harder. It supports real time decision making under time pressure, under uncertainty, when the consequences of a wrong call are immediate. That difference in context changes the entire assurance picture. Second, there are three main families of operational AI: timetabling, traffic management, rostering. Each one operates on a different timescale, each one carries different assurance requirements, each one places the human in a different role. Understanding those differences, rather than treating operational AI as a single category, is the foundation of getting the assurance right. Third, human factors are the dominant assurance concern, not the algorithms, not the data pipelines, the humans using the system. Controllers and planners need to understand the recommendations they are receiving. They need to trust the system, but not overtrust it. They need to be able to verify recommendations quickly under pressure. Poor interface design, inadequate training, or misaligned automation can undermine safety and efficiency more completely than a flawed model. The technology is only half the system. Fourth, safety integration is essential, and here I want to be precise about what essential means. Hard safety constraints: never route two trains to the same platform, never recommend a movement, the interlocking cannot authorize. These are not soft objectives, they are not trade offs, they are boundaries the system does not cross. Controller authority to override must always exist. Fallback to manual operation must always be viable. These are not design options, they are design requirements. Fifth, the assurance framework remains EN 50126, 50128, and 50129. But the emphasis shifts. In maintenance AI, the focus is on data quality, model accuracy, and operational design domain. In operational AI, the focus moves to human in the loop design, real time performance, and integration with safety systems. EN 50716 and ISO/IEC 42001 add the governance layers: data governance, model versioning, organizational accountability, change control. The framework is the same, the application is different. Know the difference. Sixth, real time performance matters. A recommendation that arrives too late is not a slow recommendation, it is no recommendation at all. If optimization takes 10 minutes when the disruption needed a response in 2, the system has failed operationally, regardless of how technically correct the output is. Assurance for operational AI must include performance testing under realistic load and realistic disruption scenarios, not just accuracy testing, not just compliance testing, speed and correctness together. Because in a live operational environment, one without the other isn't enough. 6 insights. And if there's one thread running through all of them, it's this: operational AI works when the technology and the humans around it are designed as a single system, not separately. Together, the algorithm supports the decision, the human owns it, the assurance framework holds both accountable. Get that right, and operational AI delivers real, measurable value to the railway. Get it wrong, and the technology becomes a liability rather than an asset. This lecture has been about understanding the difference
All right, that's it for this session. If you found this helpful, hit the subscribe button and turn on notifications so you don't miss the next one. And quick reminder, make sure you check out the podcast series here on the channel, Rams Ready for Everything Rams, and Safe Tracks for System Safety Assurance. If you're following along with this course, those episodes will really help connect the dots. Thanks for watching and stay tuned for the next one.